rope problem, we shortcut our scroll. Oh, I guess I'm going to go full screen. We are going to not have the same exact acronym. There's going to be a little bit of a modification. So normally we say that work is the integral of ADD multiplied by volume. And that is when we have a three-dimensional density problem. So that's 3 dimensions. But when we have a one-dimensional density problem, when we go from 3 dimensions down to 1 dimension, our acronym modifies by getting rid of 2 of those length dimensions and changing volume to just length. So with this particular example, we've got a 30-meter chain. It's hanging from a cylinder that's attached to a winch. There's no friction in the system. This is math. We ignore friction, air resistance, all those things. That's for your physics class. The density here is our important clue that this is going to be a linear or a one-dimensional density, because this is kilograms per meter. So that's a one-dimensional density. Normally, when we think about density, we're thinking about kilograms per meter cubed. So that denominator would be a meter cubed. But because that's just a meter, we know we're not dealing with this volume situation, we are dealing with that. And we want to remember that that quantity that I put in parentheses, whether it's volume or length, and later today we'll have an area in there, I put the parentheses to remind you that it's not the volume of the solid object, it's not the length of the rope. We are strictly looking at the element. This is the volume of the slice, not the volume of the whole vessel. This is going to be the length of an element of rope, which is just a little tiny piece of rope. It's not the full rope length or the chain length. So we'll see how that works. So here is our element of rope. It's just one little segment of rope. And that thickness of that segment is dy. So we're thinking of the thickness of that red line I've drawn there as dy. So it's just a tiny piece of rope, that dy. It's just a miniature length of rope, not the full length. And let's plug into our acronym. So our work is going to be the integral of A, which is acceleration, ADD, acceleration, density, depth. Our acceleration is 9.8, our density is 5, and we don't have to modify that. We had a problem earlier where it was given per centimeter or something, and we had to modify it, or maybe it was given grams instead of kilograms, so we had to modify it. Question?
Are you recording the lecture?
Did I hit record? I think I
you
did.
did.
I think I did.
Sorry, just making sure I don't.
Yeah, we'll just,
pop up.
it can't hurt to double check that this thing is spinning.
Countdown.
Yeah, we are
okay,
going.
cool.
Yeah.
Just making sure.
Never a bad idea to double check. So let's then find the second D. So acceleration, density, depth, or distance. You can think of that second D as depth or distance. Kind of depends on the perspective of the problem. And what we're referring to is the distance this element of rope needs to travel. And what would that distance that element of rope needs to travel?
30 minus y.
30 minus y. Right? So the whole length is 30. Y is that little height down there. The complementary height will be 30 minus y. So that's going to be our second D, 30 minus y. So ADD, and now with the rope or a chain, this is simple. The last part is just dy. That's it. That is the length. That is the elemental length. So like when we had the volumes on Tuesday, we had the cross-sectional area, and then we had to multiply by dy. That created the volume. Here, when we have length instead of volume because we're in one dimension, we just don't have the area piece. We just have the dy piece. And then we are going to lift all the pieces of rope, so from 0 to 30. And that will be our integral to find that work done. So let's see what that turns into. We can pull this out, so what's that going to be? 4,900, 8,000, 9,800. Does that look right? 9.5 times 9.8 times 5, just double check that for me. And then if we integrate this, we're going to get 30y minus y squared divided by 2 from 0 up to 30.
It shouldn't be 4,900.
It shouldn't be 4,900?
No, it's just 9.8 times 5.
Right.
So it's going to be like less than 50.
So, oh, yeah, that's a good point. So is it just 49? Oh, right. Normally we are multiplying by 1,000,
yeah.
not 10. In my mind, I took the 9,800. So is it just 49 then?
Something like that.
Okay, good. Something like that. It looks right. 80, 90, I can't think fast today. It's going to be a slow day. 49 times, let's see, if we plug in the 0, we get nothing. If we plug in the 30, we're going to get 900 minus 900 over 2, so 900 minus 450, which is 450. Now, whatever that turns into, somebody can do, oh, I guess I brought my calculator. So we're just going to do 49 times 450, and we'll get 22,050, and this is work, so we have joules of work. So that is how we will handle part A, where we've got the 30-meter rope and we're just pulling the whole thing up. That's how much work is done. Oh, golly, I hate that when that happens. So this is also the same amount of work that would happen if you just dropped the rope. It's just that instead of you doing the work lifting the rope up, gravity would be doing the work pulling it down to the earth. Part B modifies this a little bit. They say, hey, let's add a 50 kg block to the bottom of this thing. Now let's find the work. Well, lifting a block puts us in the simplest scenario, and the simplest scenario is where you're just displacing a block, like a point mass. So we're just taking the mass and we're just moving it. Then we just have to multiply force times distance. And force, when we're dealing with gravity, is mass times gravity. So all we have to do, if we're going to lift the block, if we are lifting the block, the work done in lifting the block is just going to be the evaluation of this. So for the block to be lifted, we're going to do mass, which is 50 kgs, multiplied by gravity, which is 9.8, multiplied by the height, or the distance traveled by the block. We're going to move it 30 meters. So there we go. So this is going to be 1,500 multiplied by 9.8. And that will be, again, in units of joules. So 1,500 by 9.8 is going to give us 14,700 joules. And then the total then, if we're up at the top, pulling up the chain or the rope and the block, we have the work that's done in lifting just the chain, and then we have the work done in lifting the block, and we just add the two together. So our total work is going to be the 22,050 plus the 14,700. So our total work will be whatever this turns into. So 36,750 joules. Any questions on that? Bless you. So the interesting thing about the chain and the rope is that it's a lot simpler than the vessels, the tanks, because you just have a dy instead of a cross-sectional area multiplied by dy. But sometimes it's just hard to. The simplest cases sometimes can be just a little, harder to conceptualize. So when you see that length, we literally are just thinking of the thickness of this segment of rope, which is a vertical thickness, which is a dy. A dy. Okay. So, and then we talked about this partial lifting of the chain. You can look at that to think of two different perspectives on finding the work in lifting the chain. And our last topic in this section is force and pressure. And what we are going to do now is find the force on a wall. And in our D2L site, also in OneNote, there's a couple of videos on hydrostatic pressure, which are really good videos to watch to get understand the concept of hydrostatic pressure. The idea is if you're submerged in water, the pressure is going to be the same. You're going to feel pressure on every piece of your body, from all directions. That's what hydrostatic pressure is. Right? You don't just feel pressure on your head. The water is exerting the same pressure in all directions simultaneously, which is interesting. So you should watch those videos if you want to get a sense of hydrostatic pressure. And we're going to use the same variables that we've been using when we're dealing with this. Whoops, I didn't need to do that. So let's take a look at this slide. So the idea, when we're trying to find the force on this wall, we are looking at the cumulative force so that we know how thick to make the wall if it's a dam. We need to build it with materials so that the thing doesn't collapse. Let me ask you one question. I don't think I asked you this question on Tuesday. If you have a dam, so you've got this wall here, water is pressing up against it, creating a force. Right, there's a force on that wall. If you have, let's say, 1 mile of water behind that dam pressing on the wall, what do you think happens to the force if we double the amount of water that's behind the wall? So we've got our dam wall here, we've got a mile of water, and then we say, hey, let's dig a trench and put another mile of water behind it. So now we have 2 miles of water pressing on that. What do you think happens to the force on that dam if you add that extra length of water? I hear a double. Anyone else have an idea? Has anyone had this in physics yet? The change is nothing. If you have a dam and you have 5 feet of water or 5 miles of water, same force. That's why they always build them as long as possible behind the wall, because it does not matter. When you think about that hydrostatic pressure where the force is going equally in all directions, you can kind of think of 2 molecules of water and they're sort of canceling each other out. The force that this one's pushing in this direction, the force this one's pushing in this direction, cancel out. So it really only depends on that film of water against the dam that actually creates the force on the wall. So it does not matter how deep, how far back the water goes, how long the body of water is behind the dam. All that matters is how deep it is right in front. That's the part that dictates everything. 1 inch of water, 10 miles of water, same force. So it's super interesting to watch those hydrostatic pressure videos because it's not intuitive. Definitely not intuitive. That it feels like it should double or even do something more than that possibly, but it does nothing.
Well, then why is there only a certain amount of water that a dam can hold?
The dam can hold as much water as you can. It can hold back as much water as the space you can dig the trench behind it.
Oh, we're not talking about flowing water.
No.
Oh, okay.
No, the water's sitting behind the
I was
dam.
so
It's just sitting there. It's just sitting there.
Okay.
Yeah, the water's not rushing.
Okay.
It's just sitting there. It's a body of water. Like that huge dam they're building in Loveland right now. whatever, and they're doing that one in Boulder, that huge, they're doubling the depth of Gross Reservoir, the water that feeds Denver. Okay, and that dam in Loveland they're building is like insane, massive amount of water. Okay, so our acronym is going to look really similar. We had an ADD volume. For force, it's ADD area instead of ADD volume. And we know that work is force times distance. If we multiplied this force by one more unit of length, we'd end up with ADD volume, which would be work. Work is force times distance. So if we take that and multiply by one more meter, we'd end up with our work integral. So same exact acronym, everything's the same. Acceleration, density, depth or distance, you can kind of think of that second D in a couple of different ways. And the idea is that we are going to do a Riemann sum again. We're going to figure out the force along a strip, so we're sort of breaking the dam into a bunch of horizontal strips. We figure out the force on each strip, add them all up, get an approximation, take the limit, and then we get an integral. So that's going to be our integral. I've gone through all the units here. Look at those on your own and try to wrestle with units of pressure, which are called pascals, which is the same thing as a Newton divided by a meter squared, or you could write it as a kilogram divided by a meter second squared. There's all sorts of unit madness. But if you look at each piece in here with the units, you will end up with a unit that is a Newton. Bless you.
Thank you.
Units of newtons for force. So let's do one of these. So we've got a dam wall, we've got the force on the wall. We want to know what that force is. So there's our acronym. We're going to draw a coordinate system here. So I'm thinking about this coordinate system. I like to draw the coordinate system right there. There's other possibilities. I think that's the most intuitive. We're going to draw a horizontal strip. And that horizontal strip, I will say, has a width of W. That's at a random Y. Goes all the way across. And the ADD part really doesn't even matter on the picture so much. The part that the picture really helps us with is that area piece, which we'll get to in a moment. So ADD. Acceleration due to gravity. Oh, that's 9.8. Acceleration. Density. Well, we're dealing with water, so we're back to the 1,000. Acceleration, density. And then how deep is that horizontal element? 15 minus y. Right? So it's the same as the other ones we've been doing. We're looking at our element, whether it's a cross-section of water or a little piece of rope, whatever it is, we just do that complementary subtraction. 15 is the full length, y is the short length, 15 minus y is the upper length. So 15 minus y. And now the area piece. And again, not the area of the face of the dam, the area of this elemental strip. The area of this strip. And the area of that strip is its width multiplied by its thickness, which is dy. So this is going to be width multiplied by dy. That is what we're talking about with area. And this will go from 0 to 15 because we have 15 meters deep of water. All right. So now we have to get that width all the way across. Our anchor into this problem is going to be to find the equation of that line on the right, solve for x, because that horizontal strip is horizontal. So we need to create an equation that measures horizontal distance, which means if we can take that right edge and solve for x, then we're measuring horizontal distance from the axis over. So let's find the equation of that. Oh, it's a line. We know how to find the equation of a line. We need 2 points. This point on the line, 5, 0. How about that point on the line? 10, 15? So if it's 20 all the way across the top, coming from the center where I've drawn the axis, it's 10 over to the top. 10 over from the axis, and then we're going up 15. So, equation of a line is y equals mx plus b. We could do it that way, or we could do point slope formula. It does not matter. Typically, when you have 2 points and one of them's not the origin, it's easier to do point slope. I'm going to pick this point because there's a 0. So we're going to do y minus 0 equals the slope. The change in y over the change in x. The change in y between these 2 points is 15. The change in x is 5. So we go up 15 over 5. So then we have an x minus 5. So there's point slope formula. This is going to be y equals 3x. So 15 divided by 5 is 3, and then we distribute, so we get this. But we want to isolate x because we're measuring horizontal. We don't want our function to be measuring vertical. We want it to be measuring horizontal. So there. That purple x is now measuring this distance right here, right? When you isolate x, you're measuring from the y-axis to the right. So what does that mean W is? How do we get to W from that?
Double it.
We are going to double it. So that, we have to multiply it by 2. So we can... So that is our integral. That's going to find the force on that wall. And that 2 can come out to the front. So we're just going to put a multiplication by 2, and then we're going to have to FOIL, or whatever you call it these days, distribute. Somebody told me that some high schools don't teach the word FOIL anymore. So we have to multiply those 2 binomials together. So whatever your technique is, first, outer, inner, last, or whatever type of distribution you want to do, there's lots of ways. So I'm going to distribute the 15 first. So 15 times 1/3 is 5, so we're going to get 5y. And then 15 times 5 is 75. And then negative y is going to give us negative 1/3 y squared and minus 5y dy. So that'll be our simplified integrand. I see some cancellation. Looks like a 5y goes away. We'll do our standard integration, power rule. Eventually we'll multiply by 2, but you never know what's going to cancel, so I always just wait. So that's going to be y cubed over 3, so that's going to be minus 1/9 y cubed over 9. And then 75y, 0 to 15. That's 0, not going to contribute anything. You plug in the 0, you get 0, so you subtract off 0. We just have to plug in that 15. See what we end up with. So 15 goes in there, so we're going to end up with 15 cubed, whatever that is, 225 times 15. 225 times 15, 3375. Oh, I guess I could have canceled out a 3. Does not matter. Plus 75 multiplied by 15. So that's 11, 25. So we've got that. Then we just have to simplify it. Add all that up. I'll do that during the break. I'll add that up. And that will be with units of newtons. So that's going to be the force on the wall. So any piece of that that you're not 100% sure about, yeah.
Where did the 2 come from?
So this 2 right here is coming from the fact that the width is 2 times that purple distance. The purple distance, when we find the equation of that turquoise or blue line and we solve for x, that's only measuring from the y-axis over. So this green axis is right there, and if we solve for x, x is just measuring that distance, but the width is all the way across, so it's a symmetry thing where there's just as much distance to the right and to the left. So the length of that full element is going to be 2 times the distance from the axis to the right. Does that make sense? Yeah.
Why do we need a? Oh, never mind.
So our goal, this whole red piece is the area of this red rectangle. So when you're thinking about this element here, you're thinking about this as a rectangle. So we're trying to find the area of that rectangle. So the area of that rectangle, no, I don't want an arrowhead in there. So the area of that rectangle is going to be the width all the way across the dam multiplied by dy is the height or the thickness of it. So that W is going to be 2 times the purple, and then multiplied by dy.
Where did the 1,000 come from?
The 1,000 comes from the density of water. So this D right here, that D is density, and the density is whatever the liquid is that you're using, and this liquid is water. So the density of water is 1,000 kilograms per meter cubed. Other questions on it?
I have a question.
Yeah.
So are you calculating the force that is being applied on this surface that you're looking at?
Mm-hmm. Yeah, so just the face there. Just that surface that we're looking at, that's the force, the cumulative force on that wall. So when we build that dam, we have to build it in a way that it can withstand that force. Plus a margin of error, of course. Let's look at a wall that's triangular. So we've got this triangular wall. And again, so we're dealing with a 2-dimensional surface, right? We're just looking at the force on that wall. Our acronym will be the same as what we just used. So for force, it's ADD area. Well, we're going to do something similar to what we just did. We're going to fill in the ADD. So our cumulative force is going to be the integral from 0 to 30. And it's going to be A, which is 9.8, acceleration, and then density. We're dealing with water again. I guess I didn't write it in this question, but we are dealing with water again. So that is the density of water. So AD. And then when we look at our element, we're thinking of this as an element at a random y right there. And so now we want to think about how deep below the surface is that y element. And it will be the total distance, 30, minus the lower distance. The lower distance is y, from there to there. So this upper distance is the total distance minus the lower distance. So 30 minus y. That goes right there. So there's ADD. ADD. So acceleration, density, depth. And then we have this area. And once again, not the area of the triangle. That area is the area of this rectangle right there. And the area of a rectangle is base times height. The height is dy. So this is going to be width. The base of that rectangle is W, and then dy. So that is the area that we're talking about. It's the area of a rectangle. So width times height. The height is very thin. It's dy. The width. Oh, we'll do what we did last time. We'll say, hey, let's put in a coordinate system. we put in a coordinate system right there. If we find the equation of this right-hand side, if we find the equation of this right edge, OMG. Even that didn't work. Okay. The right side of the triangle. We're trying to find the equation of the right side of the triangle. Technology. Love it when it works. So we are going to end up with just finding actually half of W. Because when we find the equation of that right edge and solve for x, that's only measuring from the axis over to the edge. So that's only half of W. So we will have to double that x to get the value for W. All right, what is the equation of this edge? So now this is going through the origin. And if that's going through the origin, then we don't have to deal, you could use point slope formula, of course, but you're subtracting 0 twice, then you don't have to deal with it. You could just do y equals mx. If the y-intercept is 0, the slope-intercept form is y equals mx. So y equals, let's see, the m is up 30 over 10. Up 30 over 10, slope of 3. So this will be 3x. Okay. So that's the equation of that right line. It's measuring height right now. It's telling you the height you are above the x-axis. If you plug in an x value, you're going to get a y value that measures the height above it. That's not what we want. We want to measure sideways. So all we do is isolate the x, and we get x equals y divided by 3. Now it's measuring sideways. So now if you plug in a y value, it's telling you how far to the right of that y-axis you're going to go. And then to get to w, w will be 2y over 3. We double it. And we'll plug our stuff in, pull out our constants, 9,800, 0 to 30. Let's see, we have 30 minus y. W is 2y over 3 multiplied by dy. And the 2 divided by 3 can come to the front. So we'll have 2/3 of 9,800. And then inside the integrand, we're going to distribute the y that we have there. And this will be our simplified integrand. So we're factoring out the 2/3, leaving just that y there, and that y will jump in here and multiply to each of those terms. Then we'll integrate. So we get 15y squared minus y cubed over 3 from 0 to 30. Plugging in 0, it's not going to contribute any amounts, so we can ignore the 0 essentially. Let's go here. So 2/3, 9,800 multiplied by. So we're going to have 30 squared. So 30 squared is 900. So we're going to have 15 times 900 minus. Here we're going to have 30 cubed. Right? 30 cubed. We're going to have 30. Well, 30 squared is 900. So I could write it as 30 times 900, and I could divide just the 30 by 3 and make this a 1 and a 10. Do that. And then we just have to evaluate all that. So I'll do that during the break. I'll add that all up. This will be in newtons. So that will be the force. look at that. Tell me if you have any questions on it. And I'm coming up with a whole ton of newtons. $29 million newtons, 29,400,000. If I typed it in here correctly. Any piece of that you want to ask about? Make sense conceptually? So the biggest error I tend to see on the exams is with this part in parentheses, the volume or the area or the length. Just remember that that's part of the element. It's not the whole face.
Why is it newtons since we're working with area?
Because we're force.
Okay,
So we're talking about the force on the wall. Units of force are going to be newtons.
okay.
So units of work are Newton meters, which we also call joules. So if you multiply force by meters, you'll end up with work. Yeah, so force is always going to be newtons for us. Work will always be joules or Newton meters. And so we're looking at these horizontal strips because on that horizontal strip, the pressure is constant. And so if you go down a certain depth, the pressure is going to be constant on that horizontal layer. So we're looking at strips of constant pressure, figuring out the work on each of those strips, and then adding them all up. Cumulative work. All right. So the worst shape to deal with, we've already kind of dealt with this already, is a circle or a semicircle. We are just going to set this one up because the integration is very tricky. I would never put the integration of the thing that we're going to end up with on a test. If you're interested in how to do the integral, we can do it during office hours, totally fine, but it's a very tricky integral. We'd never put it on a test. But let's get to the setup though. The setup of this is super important. You should be able to get to the setup. So the idea here is that we've got a pool and there's a little circular window so that spectators can look through the circular window into the pool. You know, like those diving pools often have this type. NASA has this type of thing. You know, they do those. They have those big tanks, and they have windows all along the bottom. You know, and you can go into those tanks and throw bowling balls around while you're 20 feet below water. It's pretty cool. So we are dealing with force. So that's our acronym. ADD area is our acronym for force. For work, ADD volume. Force, ADD area. Once again, I put a note here. Area is not the area of the window. It's going to be the area of the full strip all the way across. We want the area of that yellow rectangle. That's what we're talking about when we find area. The area of that yellow rectangle is going to be W, the width all the way across, multiplied by dy. So we're going to have a W that's going to be twice. So W is going to go all the way across. That's going to be W. And the first step is going to be to figure out, so just like the previous ones we just did, the ADD part's easy. Right? It's 9.8, it's 1,000. How deep is this element? Well, we're doing that complementary distance. If the full distance is 4 and this distance is y, then this distance is complementary distance there. The upper distance is 4 minus y. So that part comes pretty fast. The ADD part comes pretty fast. Now to get this other part, to get the area, we definitely need to find the equation of the circle. And we say to ourselves, we're measuring horizontally, so we want to solve for x. So that's what we're going to do. So the way this unit circle is positioned, it's positioned with the center of 0, 1. You can see that the radius is 1. So center at the origin would be x squared plus y squared equals 1, but we're shifting it up 1 unit. So instead of a y squared, we have a y minus 1, since we shifted it up 1 unit. So the equation of a circle in general is x minus the x coordinate of the center, x minus 0, squared, plus y minus the y coordinate of the center, so y minus 1, quantity squared, equals the radius squared. So there's our equation. Then we need to solve it for x. We want to measure horizontally, we need to isolate x. And we're going to have a plus or minus in general, but we are going to choose the right half of the circle. The right half of the circle will be the positive square root. So we square this out and we get y squared minus 2y plus 1. Put that in there and the ones are going to cancel, and this is going to be your simplified function. It's a function, but it's a function of y. It's measuring horizontal. It's not a function of x. So x is a function of y. And so then we come over here, and this right here is doubling that x value that we just solved for there. So the width all the way across, all of that is the width, and then all of that is the area of the rectangle. The 9800 pops to the front. You can distribute the 2 and you get 8 minus 2y. Now this integral is hard because when you let u equal negative y squared plus 2y, when you let u be what's inside that square root, you are not getting a match for what's on the outside. Yeah?
Why do we do 1 minus the y minus 1 squared in the square root?
Right here?
Yeah.
So we're just solving this for x.
Okay.
So if we solve this for x, this piece right here gets subtracted over, and that's right there. So we're subtracting that, and then we take the square root of that entire right-hand side, which leaves that piece inside the square root. Now technically you would have plus or minus, but if you choose the plus, you're getting the equation for the right half of the circle. If you choose the minus, you're getting the equation for the left half of the circle. We just want the equation of the right half of the circle, so we'll solve it for x, then take the positive square root. And you see here that substitution is not going to work real nicely. So the trick, if you want to play with this integral, if you want to try to do this integral, the trick is going to be very clever here. You're going to make this 6 plus 2 minus 2y multiplied by the square root of negative y squared plus 2y dy. And what you're going to do is create 2 integrals from 1. You're going to take this square root piece, distribute it to this, distribute it to this, and then that'll create 2 separate integrals, one of which you can use substitution for, and the other one you won't actually need substitution. So it's a little tricky though. So we take the derivative, it's like, oh, if we had a minus 2y plus 2, we could use substitution. So we create a minus 2y plus 2. So we just take that 8 and break it into a 6 and a 2 and group it this way and then distribute that square root and you can get to it, but it's very tricky. Very tricky. Any other questions on the setup? Everyone seen the different pieces of the ADD area? So on the next slide, it's just a more complicated bit. The book has the one on this slide in it, where the circle is hard enough, and then they decide to use a fractional radius. It's like, really? Just doing the circle is hard enough to understand, but then they decide that they're going to do it with a fractional radius, so you're going to get a bunch of fractions in your expression for the width of the element. So you can go through it and just see if you can get to this place up here, but your integral is going to look a lot like the one we just had, It's just that there's a million fractions in it. A few fractions. A few fractions feels like a million fractions when you're already in the hardest concept, which is finding the force on the circle, on a circular window. So if you want to go through it and try to get the integration, I put the answer there if you want to try to become an integration ninja, which is a goal for some people. It is a goal for some people. You want to integrate everything. Okay, so the last section, well, let me just say a couple things. So tonight, the worksheet is due by midnight. If you're having any trouble, email me. Worst case scenario, if for some reason you can't get things to work, we can figure out another way for you to submit it. But it should work pretty easily. If you have OneNote in your computer, simplest way is take a photo, upload to the computer, and then do little screenshots with the snipping tool in Windows, or with the Mac snipping tool is a little different, but it works similarly. So do that. So that worksheet's going to have practice on areas and volumes. Got to have areas and volumes down if you have any chance of doing well in the exam. So that will practice the basic skills. The worksheet is only chapter 6, nothing in chapter 7. So it's only stuff, and it's stuff that we did really in the first week and a half of class. So our last section is regarding hyperbolic functions. And we in this class, Calc 2, are going to look at just the bare minimum of hyperbolic functions. You don't see a ton of hyperbolic functions until you get into some really specific engineering applications. We are going to look at just the basics. We're going to look at derivatives and integrals. There's a whole bunch of other stuff with hyperbolics that we're just going to ignore in this class. We're just going to look at basic derivatives and integrals and see how the hyperbolics parallel the circular. So we've done the circular functions, sine, cosine, tangent, the 6 circular functions. There's a parallel universe of hyperbolics. And you all know that with the unit circle, that's how you define the 6 circular functions, with the unit circle. The circle produces the circular functions. You know that on the unit circle, cosine is first, sine is second if you look at a coordinate, if you look at a point on the unit circle. First coordinate is cosine, second coordinate is sine. So that's all old news. Now, if you're on a unit circle, we have a formula that relates the radian measure of the angle with the radius and the arc length. So, does anyone remember what S is equal to? So S is the arc length just of a sector. If you have a sector of a circle, you have 3 things. You have the angle, the arc, and the radius. Does anyone remember what S is equal to? What did you say? What?
2 pi RDS.
Something simpler. So if you have a circle, let's do it this way. The one way that I find easy to remember this formula is if I draw a sector of the circle and put the 3 things, we have that. So that's supposed to be a sector of a circle. It doesn't look very round, but it's supposed to be a sector. So this is a radius and this is a radius. Those are the same length. So the way I remember the formula is that theta is like slope, but it's circular slope. So I remember it as theta equals S divided by R. It's the circular rise over the run, which is R. And then if you solve for S, you have S equals R theta or theta R, it doesn't matter which way you write it, commutative law of multiplication. So you have that. And many people just remember S is equal to theta R, totally fine. I always have this little thing in my mind that to get the angle, do you understand that the angle measured in radians is unitless? If you understand this formula, it becomes crystal clear. S is measured in units of length. R is measured in units of length. So if you form that fraction, the units disappear. And an angle measured in radians is just a number. It's a unitless number. Which is why sometimes when you see expressions, you think, oh, why isn't the word radian in there? If you don't put the degree symbol, it means radians. If you just write 30 and not 30 degrees, you mean 30 radians. Because radians are unitless, so you don't have to put the RAD. We usually try to do it just so that it's clear. Radian comes from radius, and we usually put that in there because what you're doing is dividing by the radius. Right? You're taking the arc length and dividing by the radius to get the radian number. So you're trying to figure out how many radii fit in that arc. That's why they'll call it a radius. That's why the angle is measured in radians. You're sort of using the radius of the yardstick. So that's why it's a unitless number. That formula. Now if we're on the unit circle, if r equals 1, then the arc and the angle are the same. Which is why you will hear the expression arc sine instead of inverse sine, because arc and angle are the same on a unit circle. Okay. So, if you're on a unit circle and the arc and the angle are the same, we come over here. If we call the angle t, that means that the arc is t. So if you use t as your independent variable, cosine t, sine t, then the angle and the arc are the same. And the area of a sector is 1/2 theta r squared. The area of a sector is 1/2 theta r squared in general. Well, if your radius is 1, and if we say the angle is going to be t, we get that the area is t over 2. All right? Or you could say if you wanted to solve for t, that t is equal to twice the area. Okay, not super important. This is all stuff from unit circle, pre-calc stuff. The only thing that we are connecting here is the circular functions with the hyperbolic functions. So now we're going to take a unit hyperbola. We developed the 6 trig functions from the unit circle. Now we say, hey, let's look at a unit hyperbola. We're going to choose the right half of the unit hyperbola. And instead of points being cosine t, sine t, points on that hyperbola are going to be cosh t, sinh t, hyperbolic cosine of t, hyperbolic sine of t. And it's going to create this hyperbolic. It's not correct to call it a sector, because a sector means a piece of a circle. It means a piece of pizza. But we say it all the time, the hyperbolic sector. We just call that the hyperbolic sector. And it turns out, if you do the math, that this area here is also going to be, that area is also going to be t over 2. And if you solve for t, t will always be 2 times that area. You will never use that geometry when you're dealing with hyperbolics, but this is just how the two are connected. Both of these have the same formula for the area of their corresponding sectors. Okay, so you know the unit circle generates the primary Pythagorean theorem. Sine squared plus cosine squared is 1. Down here, the primary equation for the hyperbolics, most people say cosh and sinh. Some people say cosh and sinh. Everyone says sinh. But there's no uniform pronunciation of these hyperbolics because they're not used that much. So you're going to hear all sorts of different pronunciations. You know, in math, in Europe they pronounce things a little bit differently. It all depends on where you are. So I will pronounce it cosh and sinh. Some people will say cosh and sinh. Does not matter. No one cares. But this is where you get your primary relation. And you can see, oh, x is cosh, so it's going to be cosh squared minus sinh squared is 1. So instead of cosine squared plus sine squared equals 1, it's going to be cosh squared minus sinh squared is 1. That's your primary identity. That's going to be the main identity. That one you should know. Cosh squared minus sinh squared is 1. This slide, the top piece, you don't need to know anything from this top slide. For the homework, they might ask you to use some of these, but I will not test you on any of these. The piece that's interesting is that all the hyperbolic trig functions, cosh, sinh, I will call this tanh. This I will call cotanh. This I will call sech. This I will call cosech. So tangent, cotangent, sech and cosech, just like sine and cosine, secant, cosecant, tangent and cotangent. You will hear different pronunciations for these things. But all of them can be written in terms of exponential growth and exponential decay. Right? E to the x is exponential growth. E to the minus x is exponential decay. So the cosh function is the average of exponential growth and decay. E to the x plus e to the negative x, that's growth plus decay. Divide by 2, you averaged it. So cosh is the average of growth and decay. And then sinh, the only difference is you put a minus there. So with all of these, you could turn them into exponential functions. We're not going to do that on the test. Some of the homework will ask you to play around with the exponentials. But, so be aware of that. Down here, the pieces you definitely need to know, that is the main thing you need to know. Right there. There will be a couple of homework exercises where you might need to come refer to this. I will not expect you to memorize any of these identities. That's the only one I expect you to memorize. Other than the basics like tanh is going to be sinh over cosh, just like tangent is sine over cosine. So if you know all those reciprocals for circular functions, you actually already know them for hyperbolics, that they're the same. So you have to know the reciprocals. But that identity there is the only one you really need to know. But there will be a couple of these that the homework will ask you. Like if you're trying to integrate sinh squared, you have to power reduce it. Just like when you integrate sine squared, you have to power reduce it. So same idea. So the next thing that is probably, I think, the most useful is to get a sense of what these things look like. There is cosh. Cosh looks like a parabola, but it's not. Looks like a parabola, but it's not. You see the hyperbolic cosine every day of your life. The hyperbolic cosine is also known as the hanging cable. Back in the day, the question was, well, how do we find the equation of a telephone line that's hanging or a rope that's hanging? It is not a parabola. It is not a quartic. It is not a parabola. It's not a polynomial of any shape. You can never find a polynomial that will create the hanging cable. It is not a trig function. It is a hyperbolic trig function. Took a long time to figure out that the hanging cable is a hyperbolic cosine. The hanging cable is the average of exponential growth and exponential decay. That is the hanging cable. And they approach each other asymptotically. So the cosh is the hanging cable. It's always positive. It's above the x-axis always. It's above or equal to 1 always. Sinh looks a heck of a lot like a tangent, but it's not. There's no asymptotes vertical. So it looks a lot like tangent, but it's not. It does go through the origin, and it has the same sort of thing as tangent, where it's going above, to the right and down to the left, just like tangent. But the cosh and the sinh approach each other asymptotically along this exponential growth line, e to the x over 2. So it just gives us a visual of the hyperbolics. The cosh is the hanging cable, and the sinh is this sort of swooping, tangent-like thing. And that will help us when we're going forward. But nothing that you're going to be tested on yet. This is the important part for us. This you will be tested on. So the derivatives of the hyperbolics, the integrals of the hyperbolics, we are going to avoid these two crazy ones down here, but the others you need to know. So you need to know all of these others, so we're going to go through all of these guys, but not the crazy ones. So Let's go ahead and take our break, and then we'll zoom in on the derivatives and integrals. And you will see that there's a really strong correspondence with the derivatives and integrals of the circular functions. So it's not going to be a huge ask. It's going to take a little bit of practice, but it's not going to be too bad. All right, so we'll take 10. Yeah, question? You have a question? Oh, no. Anyone have a question? No questions. Boring. Oh, a question. Oh, let me hit pause on this recording real quick. Just get this thing. So in order to get these derivatives and integrals down, we just have to observe a couple of patterns. And when we think about the trig functions, the circular functions, I sort of break them into two groups. The primary three I think of as sine, cosine, and tangent. The primary three trig functions, sine, cosine, tangent. Even though sine and cosine are co-functions, we always sort of think about sine, cosine, tangent as the primary three. And similarly with the hyperbolics, I'll think of cosh, sinh, and tang as the primary three. All right? And the one difference that we see, we know that the derivative of cosine is negative sine. And that's the difference here. There's no negative up here. The primary three all differentiate to positive functions. And cosh and sinh are derivatives of each other. So it's not like sine and cosine where sine's derivative is cosine, but cosine's derivative is negative sine. They actually are each other's derivatives. So for the primary three, all positives. For the secondary three, all negatives. So that's the key thing to remember. For the derivatives of the hyperbolics, primary three all differentiate to a positive, and the secondary three all differentiate to a negative. All right. Sinh and cosh are integrals of each other. Integral of cosh is sinh. So all we're doing in this column over here to the right, anytime you have a derivative formula, you have a corresponding integral formula. Right? If you know the derivative of f is g, then the integral of g is f. So that's all this is doing is saying, oh, well, if you integrate sech squared, you'll get to tang. If you integrate cosech squared, you can think of the minus going to the other side, you're going to get minus cotang. If you integrated sech tang, you're going to get minus sech. So anytime you have a derivative formula, you can just turn it around and you have an integral formula.
What if you only have cosech by itself?
Then you're going to have a, so if you're integrating or differentiating,
Integrate the cosech by itself.
we'll get, that's down here and we're not going to do it.
Oh.
So we're going to skip, we're going to look at the integral of cosecant and the integral of secant. And the way that we do those, you will use as a parallel way to get to these. But we're not going to do the cosech or sec by itself because it's harder. Just like integrate, and you know the integral of sine, cosine, tangent, you know those, but the integral of secant and cosecant, I don't think anyone in here could tell me the integral of cosecant right now. Right? Does anyone know the integral? You know that if you do the pairing, like the integral of sec tan is going to be sec because the derivative of sec is sec tan. But you don't know the integral of just sec or just cosec right now, I don't think. Right, so we'll get to those. And then we're going to talk about why these are what they are down here in a moment for the integral of tang and cotang. We will see how those pan out. Just like in Calc 1, you sort of developed the derivatives of the functions other than sine and cosine by first knowing the derivatives of sine and cosine. This is similar. If we know that derivatives of sinh and cosh are each other, we can use those to build all the other derivatives. So for example, if we want to know what the derivative of sech is, from these two that we use as our base knowledge is derivative of sinh is cosh, derivative of cosh is sinh. If we use that, here's what we're going to do. So to use that base knowledge up there, we're going to think about taking the derivative of 1 over cosh. Because we can write sech as 1 over cosh. Just like secant is the reciprocal of cosine, sech and cosh are reciprocals of each other. And now we use the quotient rule. So the quotient rule says take the low function, cosh, and multiply it by the derivative of the upper function. So low is the bottom, the denominator, low and then d high, derivative of the high function, the numerator. So low d high minus high, and then d low. And d low, the derivative of cosh, is sinh. Is that the acronym or the expression most of you use for quotient rule? Low d high minus high d low divided by low squared? Is that familiar? Yeah. So that's how I'll do it in here, low d high minus high d low over low squared. There's some other acronyms that some people use. And then you divide by low squared. So cosh squared. Well, this top left term is going away because we're multiplying by 0. And so then over here, what we're going to do is just separate the denominator. We're going to think of this as that times that. So we'll separate the cosh squared into a cosh times cosh. Think about the numerator as sinh times 1. And there we have it. So now we have a negative right there. 1 over cosh, the reciprocal of cosh is sech. And then sinh over cosh is tanh. And there we have it. And similarly down here, we're going to do the same thing. We're going to write cosech as 1 over sinh. So is there any part of that first one that you're not sure about or you want to ask about? Quotient rule. Low d high minus high d low. So sinh and cosh are each other's derivatives. So if we do this one, low d high, we can probably not even write out we can probably just do it a little faster now we've done it up there. Isn't low d high 0? Because the numerator is a constant. So we can just write 0 right away. Low d high minus high is just 1. And then d low divided by low squared. So we're just going to separate it in the same way we did above. We'll just bust the sinh into a sinh times sinh, and a cosh into a cosh times 1. The reciprocal of sinh is cosech. This over here, cosh divided by sinh, is going to be cotanh. So we can generate all those other derivatives by simply knowing our 2 derivatives for sinh and cosh. Now you may, if you're into the nitty-gritty, you may say, well, how do we know that the derivative of cosh is sinh? Well, back in Calc 1, when you did the calculation for the derivative of sine and cosine, you used limits. You could use limits, but there's actually another way. Because we know that this is how cosh is defined, you actually know how to differentiate this already, right? In e, if you took this exponential expression, you know the derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times negative 1. You could actually do it that way. So if you have those definitions, those exponential definitions, you can get to these basic 2 derivatives if you care about, if you don't want to just accept it, you could go prove it, like some people would like to do. Okay. So let's try some derivatives here. Let's see. I'll do one and I'll let you do the other one. So I'll do that first one up there. Does not like it when I grab near the edge. Okay, so some practice with derivatives. The easiest thing is probably to convert this over to a fractional exponent. Generally, it's a little easier to see what's happening. So we're going to write that square root as a 1/2 exponent. And in order to formulate the derivative, we will use the chain rule. So the 1/2 comes down, and then we're going to leave the base alone and subtract 1 from the exponent. So this will be cotangent of 3x quantity to the negative 1/2. So that's the power rule part. Bring the power down, subtract 1 from the exponent. And then what's the chain rule part? Multiply by the derivative of cotangent. All right, so now we've got to start thinking. So the first thing in my mind when I'm thinking about derivatives of these hyperbolics is I always just double check, oh yeah, the 3 primaries always differentiate to positives. So sinh, cosh, tangent are positives. This is one of the secondaries, so I know it's going to differentiate to a negative. That's the first thing. So, okay, this is going to be a negative. And then it's a cotangent, which is like a cotangent. So then I jump back to cotangent and say, what's the derivative of cotangent? And maybe even that's a leap. So then you jump to tangent. Derivative of tangent is secant squared. So the derivative of cotangent is it's going to be minus cosecant squared. And so you can kind of do that little chain where you go back to the basics that you know really well. Okay, so the derivative of cotangent is minus cosecant squared. So this is going to be minus cosec squared of 3x. And then the final step?
Times 3.
Multiply by 3, yes. We have that. So there is going to be our derivative. Let's simplify this a little bit. We generally don't want negative exponents, so let's get rid of the negative exponents. So we're going to write this as 3. We could write this as negative 3 cosec squared of 3x divided by 2. And usually with the half power, we usually will write it with our square root notation. So there is our derivative. So the big thing with these, it's probably very helpful on a test to sort of write down those 6 derivatives right away, just so it's really easy to mess up the minus signs. But if you write them down, it should help. All right, you all try this one. Try the natural log one. So, in math, we don't like putting in all these parentheses, but this is really some nested functions, like that. See if you can come up with the derivative. Let me know if you're stuck. Come and give you a nudge. Double check your password. Yeah, exactly. You know where to go.
Uh,
Okay, yeah. Yeah, that's key. So there's two choices, and they may have changed.
Oh, yeah, it is a
Computer lab
change.
is on the left. So if you go down that way, computer lab's on the right. Sometimes the tech person that's in there can reset your password and check your password. If they can't, then you go upstairs, and there's a doorbell. A door with windows in it, and what IT is. And that's the last door before you get to the corner hallway with all the windows up there. So it's sort of, you have English classes. So the English department is just to the right. So if you're going that way down the hall upstairs, the English department will turn right, and the IT people are just to the left. So right at that spot. And they can usually reset it easily. Jose?
I want to receive this one.
So
See if what?
if you take a derivative of this,
Yes, yeah, if you have, yes.
that,
Let's see if that's what we really have. And I think that looks legit. So first thing that we see when we're differentiating and we have a composition of functions. So when we have a function inside a function, we're thinking of that as a composition. We always start with the outer function, take its derivative, leave everything else the same. So the derivative of a log is 1 over the inside. So we're going to do 1 over sech of 2x. So that's the derivative of the log part, 1 over the inside. Then we have to do the chain rule part, 1 over the inside multiplied by the derivative of the inside. Let's put that right in the numerator. We don't have to have like a separate thing. We'll put it right in the numerator. So now derivative of sech. First thing we say to ourselves, is it positive or is it negative? Negative. Sinh, cosh, and tanh are all positive. The others are all negative. So we know it's going to be a negative. And then we can go back to the circulars and we think, oh, it's going to be like secant. Derivative of secant is sectan. Derivative of secant, sectan. So we're going to do the same parallel move in our new hyperbolic universe. That's going to be a sech tanh. So we're going to do a sech tanh. All right. And then we have one more chain rule, multiply by 2. So I'm going to just move this negative on the outside and put in the 2 right there. And Jose pointed out that we have a common factor. We have a sech of 2x in the numerator. It's all multiplication. If it's all multiplication, you can do this canceling of common factors business if everything is multiplication. So that's going to be negative 2 times the tanh of 2x. You look so happy. Is that what you got? Almost. I'm so happy when I'm almost there. When I get close. Almost. Let's see if we can get all the way there this time. Okay, so the second one is much harder. Why don't you guys try the first one? So you guys try that one. So that's a product, right? It's x multiplied by tanh. So use the product rule. Let's see if you get that one. So with the worksheets, they're due tonight at midnight, and then what I'll do is just do a cursory grade, basically put an X or a check, and then any of the ones that are X'd, you can redo and get full credit on, turned in on the day of the exam. So next Thursday. So I'll grade them really fast and just basically do X or check, and then you'll have several days that you have to just redo the ones that are off. And Reza asked a question during the break about one of them that involves equilateral triangles. You'll need to figure out or look up, preferably figure out, the area of an equilateral triangle. That's part of it. Some algebra. All right, so carry on with your product rule. I feel like I heard something. I might have been hallucinating.
It's all towards the end.
There's an auditory.
Es que no entiendo cómo sacó esto.
So everybody remember the product rule? Is that driven into your skull? First derivative second plus derivative first second. And many people say it differently. You can say first derivative second plus second derivative first, and that works in calculus 2. In calculus 3, that does not always work. When you get to calculus 3, and your product is a product of vector functions, you have to do it in a very particular order. And so the order that I do it in here is going to be that same order to try to just reinforce that when you get to Calc 3, you have to do it a particular way. When you get to Calc 3, there's going to be a vector multiplication that's not commutative. And so there's going to be a specific order that you have to do it. So when I do product rule, I'm going to do it in that way just because I taught Calc 3 for a million years and that habit is ingrained. So first times derivative of second. So let me just write that sort of generically out first. So first derivative of second plus the derivative of first times second. So when you get to vectors, this is the order you have to do it in. So first derivative second plus derivative first second. So that is where we're just try to start further in. Okay, so derivative of tangent. First thing we say is it positive or negative? Positive. The first three functions, sinh, cosh, tangent, all differentiate to positive. So we know it's going to be positive. And then we go back and we think about tangent. Derivative of tangent is secant squared. So we've got the parallel universe, sec squared. So we're going to have x sec squared plus the derivative of x, 1. Yeah, bingo, done. So there is our derivative. Not too bad. Now this book is the first book I've ever seen that uses this notation. I don't know if this has become standard in all new calc books. Usually with trig functions, we go with the parentheses and the power on the outside. I mean, this makes sense. It's a lot like you... Oh, wait, what am I saying? Never mind, I'm lying. All the calc books do that. They do that. What I'm thinking of, what I tangled up in my mind is that this book does this, which is not common notation. They do that same thing that we normally do just on trig functions, and they do it on log functions also. So you'll see that, which feels a little weird. Normally, most calc books traditionally would do that. Yeah, we do this with trig, and this can be messy. It's really easy to kind of screw it up. So it's never a bad idea with that trig notation to do that. To really clearly see that there is a base function, cosh of 3x, with a power on the far outside. There's a common mistake, if you're not super careful here, is to bring the 2 down and subtract 1 and forget to differentiate the cosh. But when it's in this form, it's a little more in your face that, oh, bring the 2 down, leave this alone, subtract 1, and then differentiate the base. It's a little bit more obvious. And the same thing over here, when we get to the natural log and see this weird notation, if you have to differentiate, it's usually a little easier to put it in that parentheses with the outside power. You can kind of see what the outside function is more clearly. Okay, so let's go through this one. So this is going to be first derivative of second. So there's first. Derivative of second involves a power rule, a chain rule, a couple of chain rules. So it's going to be 2 cosh 3x to the 1. That's the first part, power rule part. Power down, subtract 1. Now we differentiate the base, cosh of 3x. Derivative of cosh is sinh, not minus sinh, it's positive. And then by 3. So that's the first part. So first times derivative of second plus the derivative of first, which is 2x, multiplied by the second. And that's going to be cosh squared of 3x. And there's not a lot of simplification here. Constants should come out to the front. We should at least combine those. So we'll just end up with this long alphabet soup. So there it is. There's the derivative. Slope of the tangent line to that weird looking function that we have no idea what it looks like. Unless you type it into Desmos. All right. Any questions on chain rule, power rule, derivatives in general? Okay. Now we start to get a little sneaky. Integration is always sneaky. Integration is, I can give you any crazy function and you can differentiate it. Any function, I throw in a sine, a cosine, a cosecant, a cosec, or whatever, you can differentiate it. Integration, right? Only certain functions can be integrated. There's a lot of functions that are not integrable, and it's extremely difficult to know when you're looking at a function that can't be integrated and when it can. Like that takes a lot of practice and a lot of skill. Derivatives is rote. You know your derivatives, you know your derivative rules, power rule, quotient rule, product rule, chain rule. You can differentiate anything. It might take a long time, but you can differentiate anything. Integration is totally different. We have to be stealth with integration. Now, normally, what we're going to do is try to use substitution, normally. When we have a complicated thing that doesn't have an instantaneous antiderivative, usually we're going to try to put a u in there, try to do a substitution or something. When I look at this, I'm seeing, I see a product. I see sec squared and I see tanh. Is there one of those that would make a good candidate for u because its derivative is present? So there's actually two choices here that both will work just fine. When I look at it separated the way I have the red, I say, oh, well, tanh's derivative is sec squared. Right? The derivative of tangent is secant squared. The derivative of tanh is sec squared. So that would be a natural choice for you. Now I heard somebody say secant, sec, and sec would also work. If you blew this apart a little and you wrote it as sec times sec tanh, oh yeah, if you choose u to be sec, then its derivative is present. So you could get, either one's going to give us, maybe I shouldn't say the same answer, will give us equivalent answers. They might have different functions in them, but they're going to be equivalent. So it doesn't matter which way we go. Over here, if I let u equal tanh, then du is going to be sec squared of x dx. And we will have our integral will be equal to the integral of, let's see, I let u be tanh, so there's going to be u. And then sec squared dx is du. So this all integrates to 1/2 u squared plus c. And let's keep going down here so we can, we'll do it that way too and just see that we get something that looks a little different. And now we just have to back substitute. So this is going to be 1/2 times tanh squared of x plus c. Does that method look good to everybody? So back substituting, coming, if we integrate with respect to x, we want to end up with x's, so we don't want to just leave it with the u's. Now let's do it over here with the other u sub. So if we let u equal sech, then du is going to be sech tanh times dx. And our integral will look like a little bit different. So we're letting u be this sech right here. And then this over here, sech tanh dx, that's all du. Is that making sense to everybody? So this part's becoming u. This part over here is becoming du. And once again, oh, we have the same u expression. We get u squared over 2, or 1/2 u squared. Oh, but we used a different u. So this is going to be 1/2 sech squared. Okay. Yeah.
Will this work out? Because the derivative of hyperbolic secant is negative.
Oh, shoot! Thank you. I skipped the step where I said is it plus or minus when we differentiated. I forgot that. Oops. So we're right here, sech. The primary three differentiate to positives, sinh, cosh, tanh. The other three differentiate to negatives. So should sech differentiate to a positive or a negative? Negative. Thank you so much. Spacing out there. Momentary lapse of insanity. So that's going to be negative. And so when we come back up, what we do is move the negative to the other side. So we're going to have negative du. So what that's going to put in here is when we convert to du, we're going to factor that minus sign right out to the front. So that's going to give us a negative right here and a negative right here. Thank you so much. Those answers look really different. One's got a sech, one's got a tanh. How could we show that they're equivalent? Your favorite trig thing to do? Use identities. You could come up with an identity and you could rewrite it and you could show that they are equivalent. Right. We don't care about that in here, so either is totally fine. All right, I want you all to think about this one for a minute. It can be done with substitution. So spend a minute trying to come up with the right u. Integrands that make you say, anyone find a u that worked? Find a u? Find one? What was the u you used?
1 plus cosh x.
If we let u be that denominator, notice what happens. When we take the derivative here, the derivative is going to be sinh of x. Let's go through that exercise in the mind. Is it plus or minus? the primary 3 differentiate to a positive, so sinh, cosh, tangent to positive, so it's going to be positive. Derivative of 1 is 0, derivative of cosh is sinh. That's the numerator. So the derivative of the u is present. That allows us then to write this as integral. Let's see, sinh x dx, that's du, and the bottom is u. That is natural log of absolute u plus c. So then we end up with natural log of absolute 1 plus cosh x plus c. And this is one of those ones I mentioned last week. This is in log form. Whenever you have a fraction, no matter how messy you make the denominator, let's put a sinh here, and let's put a cosh here. Let's do a cosh squared even. No, that's too messy. I don't want to do that much work. Let's do a cosine though. Let's do sinh plus cosine. If the numerator is cosh, derivative of cosine is negative sine. So if we have that, we're actually done. If we recognize that it's in log form, which means the derivative of the denominator is the numerator, this will always turn into natural log of the absolute value of the denominator. Always. Because when you let u be the denominator, if its derivative is the numerator, it's going to be right there, and that whole numerator is just going to always turn into du. So you always end up with du over u. So if it's in log form, you can always cut to the chase. And again, log form is going to be the integral of f prime over f. So if you have this scenario, this will always turn into natural log of the absolute value of the denominator, every time. Universal truth. Right. Any questions on any of that integration stuff? Question? I saw your hand go up.
No, I'm just worried.
Okay. Let's check out some more examples. All right, so integrate this. I'll give you 2 minutes to see if you can come up with a u that will work. Remember, your basic rule of thumb is, can I let u be something that has a derivative that's present? So think about what your choices for u will be and see if you can find one that works. Anyone find a u that works?
Nope, not squared.
Not squared though. Because remember, if you did cotangent squared, you'd have to bring the 2 down and you get 2 cotangent to the 1 and then differentiate by cotangent.
You can bring the 2 over to du.
But you're going to end up with too many cotangents. I'll show you. So if you let u be cotangent squared, you're going to end up with 2 cotangent to the 1 multiplied by cotangent, and the derivative of cotangent is going to be negative, and that's going to be cosec squared of x. So this whole cotangent is gone as soon as you let it, you see it? So we're not going to want to do the, but just cotangent is going to work great. So if we do just cotangent, the derivative of cotangent is minus cosecant squared. The derivative of cotangent will be minus cosec squared, and then we have a dx. So now the derivative here, we'll do the same thing that we did before with the minus. We can move that minus to the left, and we'll have cosec squared of x dx is equal to minus du. Okay, so this will be, let's see, u squared, and then cosec squared times x dx, cosec squared of x dx, that's all negative du. So we'll have that, which is negative u cubed over 3 plus c. So it's negative 1/3. U is cotangent, so cotangent cubed plus c.
Negative.
And negative. Negatives are always disappearing. Negative. That negative is. There we go.
Is it possible to use the, for u, to use cosecant hyperbolic?
Say that again for u,
Yeah,
to let u equal just cosec?
yeah,
For sure.
okay.
So let's think about that. And I'm saying for sure. There's always, there's often many different substitutions you could do. Let's check. I should say let's check. It's certainly a candidate. So if we let u be cosec, then we first say plus or minus. It's going to be minus because it's not one of the primary threes. And that's going to be cosec cotangent. And are we going to get everything? Let's see. So our integral is going to become, let's see, so cosec cotangent, so 1 cosec cotangent with the dx is going to be a du. But aren't we going to have one thing still there? Right, we're still going to have one cotangent there. So one of these coseches will be the u, and then the other one will go with the du. But the cotangent, one of them will go with the du, but we still have one remaining. So that's actually going to give us a problem. Yeah. But it's worth trying, though. That's absolutely worth trying. And that's how integration is. Integration is not a spectator sport. Integration is one of those things you try, you run into a wall, you try something different. It's not obvious. The only time it becomes obvious is when you're doing a problem you've already done. Okay, so let's do one more integration here. This one I mentioned earlier. If you have a sine squared, a cosine squared, a sinh squared, or a cosinh squared, a cosh squared, you have to use a power reduction identity. So the power up here is 2, and if you use this modification and you write it like that, now the power is 1 on cosh. Right, so we don't have a way to, like we can't integrate sine squared or sinh squared by doing add 1 and divide by the new exponent. You can't do that. You can't use that polynomial power rule. So we need to reduce the power. And when we've reduced the power here, the 1/2 can come to the front. And we're integrating cosh of 2x minus 1 dx. So we reduce the power, pull out the 2 in the denominator. Now we are going to integrate the integral of cosh, sinh, but then we have to do a modification. Sinh 2x divided by 2, right? Because there's a reverse chain rule. the inside of that cinch is a linear function. If you were doing a derivative, you'd do chain rule and you'd multiply by 2. But because we're integrating, we're going to divide by 2. And then we have minus x, and then plus c. And so we could distribute this half. There's no point in having the answer partially factored. Partially factored is not usually helpful. Doing fine? Doing fine. Any issues with that? So power reduction. Then we'll do one more here. So this is a kiln. We just want to find the volume of it. They call the hyperbolic cosine a catenary. And it has to do with, like a sleeping cat being all lazy, kind of like the hanging cable. It's kind of the laziest way it can hang. Call it a catenary. So that's our curve. And if we want to find the volume of this, we need to integrate the area function. So this is a solid object, and the cross section is this face right here. So if this area, if we can, well, I guess we can do a couple of things. So if we find this area, we can just multiply by 6, and that'll give us the volume. Right? That cross section multiplied by the depth will give us the volume. So find the area here. Well, the area of that face is going to be the integral of 3 minus cosh of x dx. We don't know our limits of integration. We could use symmetry also. We have a couple things we can focus on here. So if we do that, then we could put a 2 in front and put a 0 there. So if we find the area of that face and then the half face and double it, we'll get the area of the full face, then we can multiply by 6. Now we need to know this intercept here. So we need to set this function equal to 0 to know where it passes through the x-axis. So this is where cosh of x is equal to 3. And that is not a special inverse cosh value that anyone knows. There's only one value that we know on the cosh curve, 0, 1. That's the only one we know. Like with the unit circle, with the circular functions, we know a ton of points, right? We have all those 12 sector points, 8 sector points. We have all those points. The root 3 over 2, the square root of 3 over, square root of 3 over 2, square root of 2 over 2, 1/2, all those ones. Hyperbolics, all we have is 0, 1 for the cosh and 0, 0 for the sinh. So we only have 1 point on each of them. So 99% of the basic hyperbolic equations we can't find exact answers for. We just have to put it in the calculator. So that is going to be our upper limit. It's going to be the inverse cosh of 3. All right, so let's integrate then. We'll get 3x minus sinh of x from 0 to hyperbolic inverse, whatever that is. Cosh inverse of 3. So now, do you see that plugging in 0 is going to give us nothing? Certainly 3x, that's going to be 0 when you plug in a 0. But sinh at 0, remember the shape of sinh. It looks a lot like tangent. It sweeps right through that x-axis right at the origin. So that's the one value we know for sinh. Sinh of 0 is 0. So this all becomes 2 multiplied by 3 inverse cosh of 3 minus sinh of inverse cosh of 3. So there is our answer for the area of the face, and then the volume is just going to be 6 times this. And if we want to get an approximate answer, we just type this into the calculator. And do they give us units here? They don't. So if we want to get an approximate answer, we just type that into the calculator and we get an approximate answer. Starts to look really messy with all these inverses. Any questions on that one? Good? Yep.
How we get 12 from?
The volume is going to be 6 multiplied by the area. So once we have the area, multiply that by 6 to get the volume. So if you find the area of the face, we're going to multiply it by the depth of the kiln. The depth. Any other questions on that? Good. All right, so let's see. How do I do that here? Oh, right there. Don't like that. Let me go over here for a second. All right, so on Tuesday, we're going to spend the entire day reviewing. Today, we'll do a few examples that are super important. Let me just get this color to something that's not quite so bright. All right, so I want to do a few examples. So Tuesday, we'll spend the whole day reviewing. Test will be Thursday. And let's highlight some important concepts that we've gone over and see where you're at. So let's first look at a general solid object that we want to find the volume of. And let's suppose that we have a parabola as our base. So we're just dealing with the regular parabola, y equals x squared. And we're going to say that's up there at 4. So that's 1, 2, 1, 2. So we've got that. So there's a parabola. And we are going to create a solid object. So that's going to be the base of a solid object. So that's sitting on the xy plane. And then we're going to construct our solid object by building some geometric shape as a cross-section. So maybe we put squares or triangles or semicircles. We can do all sorts of things. Let's suppose that our cross-sections are so we have to say the shape, and we have to say whether it's parallel or perpendicular to one of the axes. So let's just go with squares. So let's just say squares, perpendicular. They love to go perpendicular. Let's go perpendicular to x-axis. So what we're visualizing then is drawing a vertical element at a random x. So it says that the cross sections are, the way they word it in the exercises, they'll say the cross section is perpendicular to the base, which of course it is, and it's very easy to get confused there. The base is that parabola, and they've got to be perpendicular to the base. If you started doing oblique cross sections, it would be very, very difficult. So even though it's sort of intuitive that, oh yeah, we're talking about a cross section, intuitively we mean that that's perpendicular to the base. But sometimes it's easy to get confused. You start saying, oh, well, which base? The base of the solid. Okay, so the cross sections are coming straight out of the board, right? We're going perpendicular to that base, coming straight out of the board. And they're squares, so it comes straight out as a square. So whatever this side length is right here, whatever we want to call it, let's just call it A, what will be the area of the square that's right there that we can't see because it's coming straight out of the board? What would the area of that square be?
A squared.
A squared. Right? The area of a square is the length of one side squared. All right, so we go to our shape and we find the area of that shape. So the cross sections are squares, so the area of a square is going to be A squared. It's going to be whatever that length is squared. Now we have to convert that area to either x's or y's. And so here's where we ask ourselves, well, is it going to be a dx or a dy with that vertical green element? Dx or dy? Dx because it's vertical, right? That's the thickness of a vertical line is dx. So we know that we want to turn these a's into x's. And that a is going to be the distance between those 2 points. Right? And that's a function because it depends on where you are. Depends on where you're drawing your green element, so it's going to be a function. And it's a vertical distance. Vertical distance is always the upper y coordinate minus the lower y coordinate. The upper y coordinate is 4. The lower y coordinate is? Yeah. So there is the area function. We take this distance A. The square, if you wanted to draw the square, it would be that distance. Like that. So you'd have an A and an A. So that square, it's right there. That is its area. So to find the volume, we're going to integrate this area, but first we'd have to FOIL this out, or whatever you do these days. Plus 16. So we FOIL it, repeated distribution, whatever. That function is the area function. It tells us the area at x. What is the x value of the biggest square? 0. This distance is going to be that's the longest possible element is right there. So that's going to create a square that's a 4 by 4. So that's going to have 16 square units as its area. So if you plug in 0 here, you should get 16. And of course we do, 16. If you plug in x equals 0. So the volume is going to be the integral. Well, let's see. The squares to the right of the y-axis are the same as the squares to the left of the y-axis, so we can definitely use symmetry. Let's go 0 to 2, but if we go 0 to 2, then we're going to double it. So we're going to put a 2 out in front. And then we'll have our function that is measuring the area in here. So we do our power rule. X to the 5th over 5 minus 8x to the 3 over 3 plus 16x, 0 to 2. 0 is not going to give us anything. Plug in the 2 and simplify. And that will be the volume. So what's that, 64? So whatever that simplifies to, that is going to be our volume. So this is called general slicing. So general slicing means you've got a base and you're given a general object that you know how to find the area of geometrically. Square, semicircle, whatever. Rectangle, triangle. Any questions on that one? Yeah?
So if you have rectangles and it says, with regard to like x, it would be like the side with this shape, how would it?
So they'd have to tell us the relationship between the width and the length of the rectangle. So they could say the cross sections, are rectangles perpendicular to x axis with W equal to, say, 2L. So the width of the rectangle is twice the length of the rectangle. And then we'd have to know where the width and the length are. And W is perpendicular to the, we'd somehow have to indicate that this is the width of the rectangle. That the width is between the two curves, between x squared and 4. So somehow they would have to describe, if we're going to do a rectangle, because a rectangle is going to have a, it's not a square. So we somehow have to indicate whether the width of the rectangle is in the board or coming out of the board. I didn't word it well, but you get the idea that we have to somehow describe which is longer, the length or the width, and then what direction it is.
Are there any limitations what shape can be?
The only limitation is that we have to be able to find the area of it geometrically. So we will see squares, you might see rectangles. Rectangles are kind of hard to describe though, but sometimes they'll give you rectangles. Semicircles, we can describe the area pretty easily. So usually you're seeing squares, semicircles, and triangles. And if they give us a triangle, they could say it's an equilateral triangle. So it'd be sitting, it'd be coming out and coming to a point right there. So they could give us an equilateral triangle like that, or they could say it's a right triangle where the legs of the triangle, are whatever. They'd have to somehow describe where they are. Because you could have a right triangle that points up here or it points up here. So they'd have to somehow describe that. Yeah?
When it comes to studying for the test, what do you recommend?
First thing I recommend is going to the prior exams. Well, after you finish your homework and your quizzes. Finish your homework and your quizzes first, of course. But then I would go to the prior exams. So remember that for each of our units, so we're in the first unit here, chapter 6 and 7. So I've got 2 prior exams with answer keys right there. So after finishing homework, quizzes, and worksheet, then I would go work through some of the problems from the prior exams. Because the exam on Thursday is going to be very similar, very similar. But this will give you a sense. So we know that there's probably, unless I decide to change some little thing, there's going to be probably 12, 13, 14, somewhere about the same exact number of questions. And you can see that the hyperbolic pieces are just the last 2 questions. And both of them are very direct. Derivative, integral. Nothing, confusing. Derivatives and integrals. So I would look at the prior exams on top of all the homework and quiz stuff. Yeah, that's probably the best place to start. That make sense? All right, well, yeah, question?
Do we have the full 2 hours and 15 minutes to take the test?
Yeah, you have the full time to take it, and usually, since there's no one that comes in after, it's totally fine if you stay an extra 5 minutes probably. So a little bit of bumper on the end, 5 minutes probably. All right, well, have a great weekend. Good luck doing math. I check my email all weekend, so if you have math questions, post them in OneNote under questions here, or send me an email. Either way, totally fine. Good luck studying. Oh, one more thing. And we'll review all day Tuesday, so as you're going through homework and quizzes, if you have any questions, bring some questions. Yes, this is all for for tonight, yes. Some area and then volume. Yep. So you don't have to, it's sort of automatic. So if we just look at this, it's just automatically going to be here.
Okay, so if I just fill it out.
Yeah. You don't have to do any submitting or anything. So I see that. So I can see here, like Jack did some work on it right there. I don't know how much work.
Well, can I just say something? I didn't paste like the paper.
Yeah.
So I just did the like, can I just send you like that, if that's fine?
That's totally fine. That's
Alright,
fine.
okay. 'Cause, yeah, next
Now-
time,
Are you using a Mac or PC?
a Mac.
Mac, okay. So if you click on your Mac, if you hit Alt equal, it'll open up the equation editor. And then you can write this in with regular, math symbols.
Okay.
You know what I mean?
Do I need to go back?
No.
Okay.
Because this is the integral from 0 to 4,
Yeah,
right?
yes.
And then that, I can totally read that. But just so you know, if you hit Alt equal, then you'll get the regular equation editor and you can use the regular math symbols.
Yeah.
And it'll look
Yeah,
that
no,
way.
it's like a
It'd
really.
be easier to read.
Yeah, I'll do that. I'll
Yeah,
do that.
totally fine. Yeah, so you can do that. Or like, let's see, what did she say her last name was, began with an L. Ravel, like, so this is what most people find will do this kind of thing. Do it on paper, take a picture of it, send it up to their computer, and then do snips of each of the things and put them in. So that's sort of it's the easiest way for me to read it. But if you also use the equation editor too, that's totally fine.
Yeah.
Totally fine. The thing that is hard is that in OneNote, if you use ink on there and then you have to stretch the page because you need more space, the ink doesn't move with the page. So then the ink becomes disconnected and it's a pain in the neck.
Okay.
Which is why I don't recommend just writing in there. Now, if you're not going to make any mistakes and you can write in there and you don't have to stretch and need more space, then it's fine. But this method or using the equation editor method's probably better than just writing in it.
Okay.
Yeah.
And then the quiz, do we do it on our own or is
So
that for Tuesday?
So the quiz, the My Math Lab quiz, you just do on your own.
Okay.
So that due date is Tuesday night.
Yeah.
Tuesday night, yeah. And you'll have two attempts at it.
Okay.
So you can take it twice, and yeah, you just do that on your own. You don't have to turn in any work.
Okay, cool.
Yeah, so this is the only written work. And this helps me so when I can see the written work, I can give you some feedback before you take the exam. That's the idea.
Awesome.
Yeah.
All right, cool.
Other questions?
Nope, I think that should be it.
All right.
Thank you.
All right, good luck studying this weekend. We'll review all day Tuesday.
And it's on, you said it's on Thursday.
Thursday. Yeah, Thursday,
So,
same place.
in my case, I'll let you know probably Wednesday.
Yeah, have a good weekend.
Tuesday or
Yes.
Wednesday?
Yes, so you'll have to make an appointment up there. You've done this before?
No.
So you can go to and I think that they want all appointments now done through their website. So if you just go to the Front Range website and you type in the search thing, testing centers, and go to Westminster Testing Center and you can just make your appointment. There's always space. Definitely do it as soon as possible now. And have it start, I'll have it up there, before 9, what time's our class start, 9:30? I'll have it up there before 9:30 on Tuesday, or on Thursday.
Yeah.
On Thursday, so.
Cool.
Yeah, make the appointment, let me know when it is, just so I'm aware of it. And that also triggers a reminder that I need to take it up there. So it'll be there for you.
Okay.
And then I'll get it, you get time and a half.
Yeah.
So I'll get it that same day. I'll get it on Thursday. Sometimes I leave a little early Thursday. If I don't get it Thursday, usually they'll email it to me if I need it. So I'll have it graded by Tuesday. Cool. Very good.
Thank you.
You bet. Have a good afternoon.
You too.